this question, maximum number of balloons. Then there's the other question that we'll go through is next permutation. One is easy, one is medium. So both actually, I wouldn't say it's hard. For this next permutation, it's actually a bit harder, but I'll explain it in simple words later on. But let's just do this one first. So what this question is actually very simple. Everyone is given a string. So let's say we're giving this as a string as an input. So you can see a string as an input, and the program wants us to use the characters of text, which is NLAE, blah 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 here, all these characters, to form as many instances of balloon as possible. So for example, like in NLAE, BOLKO, like in this string itself, how many balloon can we form from here? So let's say in order to form a balloon, right? So let's just type balloon. So in order to form balloon, we need 2B. Okay, let's just say we need 2Bs, 1B, 1A, 2L, 2O, and 2N, and 1N. Okay, right? So in order to form the word balloon, we need 1B, 1A, 2L, 2O, 1N. So how many N do we have? We have 1N. Okay, so let's say we have 1B here. Okay, right? We have 1A here. Then we have 2L here. We have 2O here, and then we have 1N. So in this part, we can form one balloon. So we can form one balloon. If you look at like the criteria to form one balloon is basically this. So in this word, we can form one balloon. So let's look at the next string. How many balloon that we can form from like this text. So let's just count. So let's say how many B here. So we have 2B. We have 2A. Okay. We have 4L. Okay. We have 4O. And then we also have 2N. So from here, we can conclude that this can form two instances of the word balloon. This can form one instance of the word balloon. So this is how we can. So basically, this is how we count now, actually. And if you compare, how do we actually know that this one can form one balloon and this one can form two balloon? It's because the ratio. If you look at the ratio, you can see that 1 to 1, 1 to 1, 1 to 1, 1 to 1, 1 to 1. So let's say this is the ratio for this is 1. Ratio for this is 1. The ratio for this is 1. The ratio for this is 1. The ratio for this is 1. We are comparing it with the word balloon. So like 1B, 1B. So 1 to 1 is 1. 1 to 1 is 1. 2 to 2 is 1. 2 to 2 is 1. 1 to 1 is 1. So from here, we can conclude that we can form one instance. So we always want to get the lowest. So from here, like we can say like 2 to 1, the ratio is 2. Like 2 to 1, the ratio is 2. 2 to 1, ratio is 2. And then 4 to 2, the ratio is also 2. 4 to 2, the ratio is also 2. And 2 to 1, the ratio is definitely like 2 lah. So this is why we can form two balloons. So what if like in a case where let's say we have something like these. Say I just put more O, and then I put maybe more N, and then I put maybe more L. Okay, so in this case we have 2B, then we have 2A, but now we have 5L. Yeah, we have 5L, then we have 5O, and then we have 3N. So in this case, how many balloons that we can form? So 2 to 1, 2, 2 to 1, 2, 5 to 2, so it's 2.5, right? And then 5 to 2, it's also 2.5, and like 3 to 1, it's 3. So the question is, we have different ratio here. How many balloons that we can form? So if we were to form 3, we don't have enough B, we don't have enough A. So, and we also don't have like enough L. So the thing is, we always take the lowest ratio. So we can only form like still 2 balloon only, because we only have enough characters for 2. So this is basically a question, and this is like the whole like algorithm to this thing. So the way that we can do this is where we have to form this first, like these references. So we are going to use something called a hash map. So in C++, we can call a hash map like this, an ordered map. And so I want it to be char int, so I can call this required. And then I can just form the hash map here. So why char is like, because we are looking at characters. So B is one character, A is one character. And int is because we are looking at the count. So like for the word balloon, you have like 1, 1, 2, 2, 1. So I'll just form it like this. So B takes 1, and then A takes 1, and then L takes 2, O takes 2, and N takes 1. So this is basically the hash map, our reference map. So now we just have to go through this text and form the other map. So let's just form another map, an ordered map. This is also of type char in. I'll just call this count, and I don't want to initialize it because it should be empty at first. I haven't populated the map yet. So then we can look through the text. Let's just we can use the for each loop actually. So in this case, we can actually use a for each loop. Then it will be easier for us to process. So we can just do a for each loop. So if count dot find. So let's say so what are we trying to do? So we want to add how to say, so like going through this text, we want to look only for this character. We want to only compare B, A, L, O, N. But there's a lot of like garbage here, right? So like E, for example, E, we don't want E, and K, we don't want K. So we only want to look for B, A, L, O, N. So we have to have an if case. We only want to add B, A, L, O, N into this count. So of course we can do like if C equals to like B, then we add in or something, but like that would take a very long. Since we already have this map, we can just use it. We can just say required.find. If I were to find C and it's not equals to required.end, things like this lah. Then I can just add it to count E. Okay, I can just do this count C++. So what does this mean is where I'll just go through each character. Let's say I'm at end, and then I'll just check. Okay, is required here? Does required here has n? So not equals to required.n means like required.n means like I cannot find it. So if I can find it, then I just put it into count and I increment the count. So everything in the count initially is 0. So if I do plus, it will become like B will have 1. And I'll just keep on going through. So basically that's the idea. And let's just so this is like populating. I'll just leave populating count. That's what we call it. Then after we have populate the count, what we do is where we have to calculate the what is it called? We have to calculate the ratio, right? We have to calculate the ratio. So in order for us to calculate the ratio, we have to do something where some sort of like a division, right? Some sort of like a division. So and also think about it. So what we can say is like we can just check. Okay, so like there's one thing that we can optimize. Like let's say we always need at least one, at least or two, at least, or something. So we can actually check. So we can just go through like we can look through a map also. So I'll just use a for each loop here. It will be easier. So let's say I'll just call this IT of like count. Then so I'll check if like the count, if IT of like I think it's second. Is it? Let me check. Iterating through an map. I'm not quite sure whether the syntax is correct lah, but I think it's something like that. Just check that again. Yeah, it's actually IT.first. Yep. So it's actually something like that. Okay. So I think the first is the. I think the second is. Just check. Not wrong. Yeah, they have the second. Yeah, basically that's it. So there is a lot. So like if the second is equal to 0, means like it's then we can just return 0, right? Because we cannot form. We would not be able to form. How to say? We will not be able to form a balloon if we have like 0 count. But because it is uninitialized, you can see like count is uninitialized. So if you do equal to 0, this will give you like some sort of like error because it's not going to be equal to 0. It will be like nil pointer or something. So we cannot use equal to 0. We have to do something we have to use this dot find function. So this dot find function would help us to find like if whether it's there. If it's not there, it will return like required dot end. So we can just do count dot find, say count dot find. Oh, actually we don't need, right? Wait, think about it. If count dot find okay, I think I have to reference back. I have the thing here. Yeah, okay. Yeah, we actually have to. Yeah. Okay. We actually have to like. Yeah, it's still the same thing. We have to like check if it exists. If like okay, the idea is like because we cannot have 0, right? We cannot have like B0, A0, but we cannot check for 0 because it's uninitialized. So if you check for 0, it wouldn't give you the correct result. But we can compare these two hash map, like whether this hash map and this hash map have the exact same keys. If they don't have the exact same keys, then we know it's not correct. Like for example, here I have BALON, right? And then maybe this count only have like BAON. Then it's not valid because you need to have at least L. So the way that we can do it is because we can just look through required. Then we just check like if it has the first is equals to like count dot end. If it's equal to count dot end, we just return 0 because like that means equal to count dot end means I cannot find. That means like one of it is missing. Let's say either B is missing, A is missing, L is missing, or something like that. So this is what we can do. Like we can just return early. Else then we can just calculate the ratio. So I will just say calculate ratio. So I also have to like look through the count. Then what I'll do is I actually have to initialize like a value first. I'll just call this lowest ratio, and I'll just return it like lowest ratio. Okay. From here we can actually check. Okay, if we can check the ratio. So like this lowest ratio lah. Because we want it to be a very, we can actually like initialize it to -1 first. Yeah, we can initialize it to like the -1 first, or we can use some in max like the maximum, like the largest integer, because we want to look for lower. Yeah, so actually we should use in max here. We need like a largest number possible so that we can compare it. So the ratio, how do we calculate the ratio? It's basically very simple. We can just do IT second divided by I think it's required second, right? Yeah, you can just index it into it like an array. You can index it like this, and if this ratio smaller than lowest ratio, then we can just assign that lowest ratio to equals to this ratio. So that's how we can do it. Then in the end we can just return lowest ratio. Let me check if this is actually correct. I'm using, oh yeah, actually this is, yeah. So I think this is correct. So that's what we're going to do. So let me just revise this. We have a base reference for the hash map of like, okay, how many counts that we need to form a balloon, the word balloon. Then we have a count that will keep track of like the current count of the text, like this one, like basically something like this. We're forming like a hash map. So what 1B, 1A, 2L, 2O, this stuff is the hash map. We're trying to populating them, look through the text and then just populate the count. So we just check if all required characters exist lah. Okay, we want to check like, okay, the count must have BALON. If it doesn't have like BALON, we can just return early, and it cannot form a word, so we can just say return 0. Then lastly, we will have to calculate the ratio, because what we do here is, for example, in this case, we always use the lowest ratio. So even though like there's like 2.5 or like 3, but we still use the lower ratio because we only have like enough number of B to form 2 balloons. So this is how we calculate it. We just take the number of count divided by the required, so then we know the ratio. So it's like I'm using 2.5. I'm using 5 to divide 2. That's how I got 2.5. I'm using 3 to divide 1. That's how I got 3. But I'll only use the lowest one. I'll only use the lowest ratio. That's why we are assigning it like that. So we can actually run this. I hope there's no syntax error here. Okay, yeah, definitely. Stuff doesn't just work as... Oh, yeah, hash mark, I have to do it like this. Okay. Basically, I'll just have to prefix them this. Oh, I don't have... I can just do this. And... yeah. Oops. Never mind, I'll just do this. Okay. So, yeah, I think... Is it like that? Oh, yeah, too used to JavaScript. We do it like this. So this is like, we do the hash map like this. Okay, great. So I guess this works. Okay, it's not a pointer. IT is not a pointer. Okay. Then we can just use dot here. Like, yep, because IT is not a pointer type. Or I think because we taking memory reference. Okay, sure, fine. Yep. Okay, great. So it works. Okay, this should. Yep, ta-da! It works. So basically, this is the solution for the hash map solution, and this is actually I would say like this kind of question is quite popular. So the key to this problem is that you have to know how to use hash map. So yeah, so basically that's it. And since I have the whole today, let's just move on with the second question to next permutation. So this one is actually harder. Let me just maybe just leave it on my previous first. Yeah. So this one is a bit harder, I would say. So how to say it's harder is where it's to understand the problem, it actually takes a bit of time. So for example, you're given an array like 1, 2, 3, and I'm not sure whether you all have like learned MF before. Like if you have learned MF before, there's something called permutation and combination. So like NPR or like NCR, something like that. Like I think the formula is something like that in MF lah. If you have learned it in your SPM. So there will always be a different type of permutation. Like permutation means the possibility. So for example, for an array 1, 2, 3, it can be arranged in many different ways. It can be arranged in 1, 3, 2. It can be arranged in 2, 1, 3. It can be arranged in 2, 3, 1. It can be arranged in 3, 1, 2. And then it can be arranged in 3, 2, 1. So all these are the number of permutations. So if I'm at 1, 2, 3, and then 1, 3, 2, and then 2, 1, 3, 2, 3, 1, then 3, 1, 2, 3, 1, I can just say this sequence of number has 6 permutations. Like, yeah, so like you see like 1, 2, 3, 4, 3, 4, 5, 6. So there's 6 permutations. That means 6 possibilities on how we can arrange this array. So the question I want us to do is, given a sequence of number, it's like an array lah, 1, 2, 3 lah, find the next permutation. So find the next in sequence. So like 1, 2, 3, the next one will be 1, 3, 2. And then after the 1, 3, 2, it will be 2, 1, 3. So you can see like at the last one, at 3, 2, 1, the next one will be the beginning one. It will be 1, 2, 3. So this is what the question wants. So why is it hard to like to understand the question is where there's this term that they call in lexicographical order. So what does that even mean? Is that everything must be arranged in a way that you cannot have like permutation sequence like this. You cannot have like 2 at the first number and then 1 in the middle. You have to follow the increasing order. So it must be from like 1, 2, 3, the smallest number, to 1, 3, 2, the bigger number, 2, 1, 3, the bigger number, 2, 3, 1, bigger number, 3, 1, 2, bigger number, 3, 2, 1, bigger number. So you from smaller to biggest. So it's like increasing order lah, but then it's called lexicographical order is where you don't measure it by because 1 and 1 compare the same, 2 and 2 compare the same, 3 and 3 compare the same. So you have to compare like this. Lexicographical order means something like this. So if you compare like this value that they combine, 1, 2, 3 is smaller, is the smallest, 3, 2, 4 is the biggest. So this is what they call like lexicographical order. So this part may be a bit hard to understand, but if you understand the problem, it's actually very straightforward. They give you a sequence of number. Basically, they want you to find the next permutation in the array. So there are several solutions here. So the one of this we can do a very slow solution. It's where we call brute force. So a brute force is where you try all the possibilities, because you have 6 possibilities, right? You have 6 possibilities, right? So you can just like look for all the possibilities. So I can just form all these 6 arrays. Then I just look for, okay, I have 1, 2, 3, right? I just return the next one, right? I have 3, 2, 1, right? Okay, I just return the next one. Basically, that's the next permutation. So we can use a brute force. So brute force, but it will be very slow. It's very inefficient, because like if we do like let me show like a scientific calculator. We have like the permutation sign here. Permutation. I hope they have like this calculator. So yeah, so if the total amount in a set, so let's say if we have 3, I think like okay, so let's say you have 2, is it? Okay, so let's say if we have like 3 and 2, so then we'll have like 6 possibilities, right? So this is permutation. Is this? I think this is permutation, or is this combination? Oh yeah, so permutation is 6. So so that's the thing. So we have only 6, but what if we have like 5 numbers, like 5 in a sequence? There could be like 20 possibilities. Then say with like I don't know, like we have like long number, can have 380 something possibilities. So if you were to do like a brute force, it's very slow, because like you have 380 possibilities. It's like if you scale this up to like, let's say 2000, it increases exponentially. It will be like some super huge. You have to go through like 4 million possibilities. Then you just look through them. It will do a very inefficient. So I will just straight up tell you there's a solution for this question where you can complete this very quick in all of n time. So don't ask me how this algorithm works, but like it's a pattern, okay? It's a pattern. So we can look for pattern from here. So if we study this enough, you can see like, okay, say 1, 2, 3 and 1, 3, 2. What changed? The number, like they swap places. Basically, the value doesn't change. It's just that the position changed, right? So, and then there's a pattern in how the position changed. Because if you think like, if you arrange everything in lexicographical order, then you cannot change too big, what? Like if you say it's in lexicographical order, I cannot suddenly the next sequence can be become like 3, like 3 in front. Cannot. You have to like, there's a pattern. You have to increasing it like smaller step. You have to like, okay, like if I put it here, like 1, 2, 3, the next one can only be 1, 3, 2. You have to like increase it at a smaller step. So there's a pattern here. So if we are able to capture the pattern, we can actually solve this very quickly, because we don't have to know the other permutation. If I know the pattern, I can actually predict what's the next, because I understand the pattern. So in order to like, there's a pattern here. So what pattern that we can observe and what we can see is, let me just record down the characteristics. Thing is, it's just changing position, okay, not value, and the next like that next permutation must be slightly bigger. Okay, it cannot be very bigger. It has to be like just slightly bigger. So there's only one possibility, which in this case it's slightly bigger. So and like if we look at at a longer number, let's say we take an example of like 1, 2, 3, 4, 5, 6, 7. Okay, let's say I change this order a bit into like say 2, 1, 3, 4, 5, 7. And then if we were to calculate with our own like brain, we can deduce that the next permutation be 2, 3, 1, 4, 5, 6, 7. Okay, why? Because like I told you, it's just a changing of like it's just a changing of position. So maybe I take another smaller array. easier to understand. So like let's say 1, 4, 5, 3, 2. The next permutation for this would be let's say the one like 1, 4, 5, 3, 2 lah. Let's say okay. Let's say 1, 3, 5, 4, 2. Okay, let's say 1, 3, 5, 4, 2. So from here, if we look at lexicographical order, like the next bigger number I can take, okay, 1 still remain because I cannot put 2 here, it will be like a lot bigger. And then I tried to remain the 3. Okay, can I remain the 3? Cannot, because why? Because like the next number is 5. So I cannot put like 4 here, I cannot put 2 here because it will be smaller. So then I have to change 3. So what's the next bigger number for 3? It's 4. So, and then I cannot put 5 because it will be like very large. I cannot put 4, very large. So I can put 2, 5. So this is actually the next permutation. So 1, 4, 2, 4, 5. So the pattern is, you can see that I was like thinking, I was comparing, okay, is this the next smallest number that I can put? And there's one pattern that you can look at here. You see that at the back, okay, sorry, this is not 4, this is 3. You can see that there's always a number that change position, okay? Like 3 and 4, they change position, right? Then 5 and 2, they also change position, right? So we can leverage this pattern and like code like a more efficient algorithm. So the pattern here that we can observe that we can use to like develop like a faster algorithm is where we can swap places, right? We can swap places. So what are we swapping? Like what's the criteria that we want to swap? So we have to check, okay, so from here 3 and 4, right? You always want to find the number that is the biggest from like how to say, like okay, you always want to find the number that's like the okay, it's sort of like reminding us of like the valid mountain question. Like okay, let's say if I start from 1, I move on to 3, I move on to 5, it's still strictly increasing, right? And then move on to 4, okay, shit, it's not increasing anymore. Then okay, I found this. So this is the pivot. So actually we are looking for the highest point. Okay, if you think of this like a mountain array, we're looking for the highest point because the highest point will always change. Why do I say so? If it's a pattern, the highest point will always change. So like 1, 2, 3, right? The highest point is 3. It will always change, become here. And then like 2, 1, 3, the biggest value is the highest point is 3. It will always change. And then in 3, this pattern doesn't like exist anymore. Because why? Because 3 is already the largest. So we can ignore 3 and look at like the next largest. So like it's 2. Okay, then 2 will always change. So this is one pattern that we can find. So we would have to find like I would call this like a pivot. We want to find a pivot so that we can actually swap places. Like pivot is like a point where you can swap things. So how many pivot are there? So like the highest point is 1 pivot, so there's 1 pivot. And then there's also another pivot where after I swap the 5, right, I have to swap any other things. So there's 2 pivot. So I like to call them as like I call them like the first black sheep lah. It's just a funnier way to call them. Then it's second black sheep. So like what's the point of finding the first black sheep and the second black sheep? Is where if you find these 2 pivot, you can just change the array. Like you can just swap position and everything will be correct. So for example, in this case, let's say I'm looking for the first black sheep. So 1, 3, 5, 4. This is the highest point, right? I want the element that is behind the highest point. So like 4, I'll say like okay, the first black sheep would be FBSR, be 4. It will be 4 lah. Okay, so this is the first black sheep, and then I want to find the second black sheep. How do I find the second black sheep? Is where I'll have to like maybe it's harder to like say like this. Let me just get my code. It's easier to like explain in terms of that. Where's my, yeah, I think it's under, let me just do like a search. What is this called? It's called next. Okay. It's under, okay, array. Next permutation. Okay. me just zoom this in. So like I say, first BS is not bullshit lah. It's like black sheep, okay? Like first black sheep. So I have to find the first black sheep. So like I said, so let's say in like 1 3 the okay 1 3 5 2, right? Then I'll have to find the first black sheep is where it's the element that after the highest point. So like 1 3 5 highest point, right? Then 4 is the first black sheep. So how do I know that? Like, okay, how can I do this? Is where I can actually, like, you can find both ways. Like, you can start from the beginning or you can start from the back. Because start from the back, you will just find at a higher point, and then it's 1 before it. Or if you start from in front, they will find the highest point that is like 1 behind it, like that. 1 is in front, 1 is behind. So like in this case, I find it from behind. So that's why I'm starting the array starting from 2. So from 2, right, I'll just look for whether the element in front is actually smaller than the current element. So like let's say I minus 1. Let's say I minus 1. I start at 0, 1, 2, 3, 4. So 4. So at index 4 is 2. So this is 2. And then at index 4 is actually index 4 is actually not index 4, sorry. Index 3 is actually 4. So is 4 smaller than 2? No, right? So it's not the first black sheep. So then it's like 5 smaller than 4. So it's not. It's 3 smaller than 5. So yeah, okay, so 3 is smaller than 5. Then I know this is the first black sheep, which it will be number 3. So in this case, you can see like we always find like around the highest point. So this is like it's just the matter of like you find from behind or you find from front. So in this case, you find like the 3 is the black sheep. So then we have to find the second black sheep. So second black sheep is actually just something that is like bigger than the first first black sheep. Sorry, I think it's 5, not 3. I was a bit blur. Let me check. Okay, let's just run it through one time. So I minus 1 is we're coming from the back. So this is 4. It's 4 smaller than. Okay, so sorry. Is 4 smaller than 2? No. Is 5 smaller than 4? Yeah, it's 3 smaller than 5. But yeah, it's something like, okay, we just want to find the first black sheep. I'm a bit like, okay, let me just, and okay, so this is 3, and we find the second black sheep. It's actually always like around the highest point. So like, it will always, like, okay, the problem with first or second is actually doesn't matter. I just want to make this clear, like there's always a pivot, but you call this pivot the first pivot or this is the second pivot, doesn't matter lah. As long as there's a pivot. So the first pivot is like 1 before like the highest point, and then the second pivot is like the next element behind like the first pivot or like the second pivot. So in this second part, we are looking for the second black sheep. So we only want to find number that is like up to the first black sheep. So let's say if the first black sheep is like 3, then we just want to find like up to 3. So we don't have to find 1 because there's no point finding 1. Like, because we know that like in next permutation, the 1 doesn't change. Because like in this case, if I change 1 to 2, it will be not slightly bigger anymore. So yeah, so we always find just up to like the black sheep. So if I find up to like the black sheep, right? I want to compare like current. Is it the big? Is it the number that I'm finding is bigger than 3? So like 2 is not bigger than 3, right? 4, yeah, 4 is bigger than 3. So basically, this is the black sheep. Yeah, this is the black sheep and this is the black sheep in this case lah. So I'll just swap them. If I just swap them, right, it will become 1, 4, 5, 3, and then this is still not the next permutation. The reason because it's like it's 5, 3, 2. So actually we want 1, 4, 2, 3, 5. And then how we can do that? You can see that like from 5, 3, 2, right? We can just reverse the whole thing. Like we reverse from 532 become like 235, then it will be the correct one. So like maybe I'm not really clear about this black sheep part. It's actually the main part about this algorithm is that you have to find two pivot, swap them, then just reverse it. So like, the point of finding a pivot is where you want to find like where you want to swap the places. Like in this 1, 2, 3, the pivot would be 3 and 2. So just swap 3 and 2, right? So like something like that. So in this case, you want to swap 3 and 4. And then you just reverse the whole thing. So it's that kind of stuff. So probably I should just like put it out one time so it's easier to like understand. I don't think I'm explaining very well here. So what is max? Actually, this max is just a value lah, that if you want to compare that. But I don't think I'm using it here, so it's actually doesn't matter. But we have to, let's just say FBS and second black sheep SBS lah. Okay, so we just initialize it to something like -1 because we don't want to mess with it. So I'll just look for the first black sheep. So let's say we start from the back lah. Okay, in this case I really start from, let's say I start from first lah. I start from the beginning. I equals 0 and then I smaller than num dot size and I plus plus. So I'll basically just run through the whole array. Okay, I'll check for this condition. So like I want to check for the reverse condition. So like if here is looking for smaller, then actually I'm looking for larger. So I minus 1 is larger than I. Then I'll just do that. Now I'll do break. So let's say let's run through one case. So let's say 1 3 1 3. What's the example that we use? 13542. 13542. I'll go from 1 and then I'll check if actually I have to like start from 1 because I'm doing I minus 1. So if is this like 1 bigger than 3? No, right? And then is 3 bigger than 5? No, right? And then is 5 bigger than 4? Oh yes, 5 is bigger than 4 definitely. So I will take like the one that is how to say before. So it will be like I think this is like 3. Wait, am I right? Let's just run it through again here. 1 3 5 2. This is start from the back. So it's 2 smaller than 4. So it's 4 smaller than 2. No, it's 5 smaller than 4. No, and then it's 3 smaller than 5. Yep, no. So that's why we're taking 3. Oh, I actually shouldn't take I minus 1. I should take I. Is it I minus 1 bigger than, sorry, let me check it through. Okay. Is 1 bigger than 3? Oh, is 3 bigger than 5? Oh, is 5 bigger than 4? So 5 is I minus 1. Num is I. Actually, I can still check. Wait. Okay, I think I'm confusing myself here, but let's just do it from back. It's actually the same thing. Just do I bigger than 0, I minus 1. So this case still stand the same. Just do I minus 1. From the back, so let's start from 2. We go to 4. So I minus 1 would be 4 smaller than 2. No. 5 smaller than 2. No. 3 smaller than 5. Yes. And then the 3 is the So yeah, this is like coming from the back. It's the same thing whether we come from the front or back. So for this part, like if we look for if no black sheep, so this is a special case. We'll go through that later. But we want to find the second black sheep. So the second black sheep, because like we already know like 3 is the first black sheep, right? The second black sheep will be always the number that is like slightly larger. So in this case, slightly larger number is 4. So that's why. How do we find the slightly larger? We can just start from the back also. But in this case, we want to look for not I bigger than 0 anymore. Because why? Because like I bigger than 0 is going to search through the whole array, and we don't want to include 1. We want to include only until the first black sheep. So we could do I bigger than the, what is it called, the first black sheep, and do I minus minus. So we only find the integer that is like slightly larger than 3, which is a black sheep. Then we'll just do like if nums I minus 1, it's okay, going to from 2 to 5, slightly bigger, right? So we have to compare it to the what is it called? We have to compare it to the first black sheep. So we want to find like the number that is like first larger than the FPS. So if it is larger than FPS, we just assign it to like that. You can break out from here. So say if we run from the back, so it's 2 bigger than 3, is 4 bigger than 3, yes. So we just sign it, then we break. Okay, so then now we have found like the first black sheep is 3, and then the second black sheep would be 4. Yeah. But this wouldn't be the actual value because we are storing their index. So in this case, their actual value would be 1, and then this actual value here would be 0, 1, 2, 3. It would be 3 lah. But the value that we are pointing at is 3 and 4. It's just that because FBS and SBS is storing the index. So after we found like both of them, we just want to swap their places. So we can just say swap nums at FBS and nums at SBS. So after we swap their places, right, it will look like this: 1, 4, 5, 3, 2. But this is not the next largest because behind here is still not good yet. What we have to do is just reverse. We would just reverse it. We would just reverse it from 5 onwards to 3, 2, 1. So it will be from like the how to say the first black sheep's index to the end. So like, so I want to like just swap here, right? But if I were to do, let's say if I were to do reverse nums, it will reverse the whole thing. But that's not what I want. In C++, you can like mention by giving it the index length. So let's say I can do like nums.begin. Because it's a factor, I can do nums.begin. So nums.begin actually just points to start, and then I can just plus with the SB. In this case, if you swap it, yeah, then it will be the first BS index until nums.end, which is first BS. Now it's like first BS, like because we swapped it. Like remember, first BS is like the number of index, so it's 1. So you can start from 1 to the end. So like 0, 1, and then this is not included from here to the end. So it will just reverse there. Then it will become 1, 4, 2, 3, 5. That's it. Then because it's a void function, so we don't return anything. This should be correct, but there will be a case that it would fail. I'll bring that up in a so yeah, your output. Did I just not mutated thing? Oh, I need to do +1, yeah, because we want to do from, so this is index 1. We don't want to change this. We want to change from here on. We have to. Yep, okay, so this is correct, but there's a case that it would fail or it doesn't run. So let's say if we try with 3, 2, 1, right? Next permutation we should get is 1, 2, 3. Yeah, see, it's not going to work because in 3, 2, 1, because but it's a special case. If you know that like it's if you can't find a black sheep here, you know that it's the biggest one, because like the logic, the pattern of finding a black sheep is that you find the biggest point and then there's a element behind it that's smaller than it. But here you can't find that point. Like there's no, if you were to visualize this this array will be something like going downhill and then there's no pivot point. But like for 3, 1, 2, there's like the highest. How do I draw this? 3 Okay, think about it. How do I draw this? Like it's okay. So the logic. Okay, let's just go back to the logic of finding a black sheep. Is where we want to find something that's smaller than the current value. So if you were to find something that's smaller than current value, like 3, 2, 1, it's all strictly decreasing. There's no point, like the peak. There's no peak because it's all strictly decreasing. And then if you look for like the first one, it's always strictly increasing. So there's no like actual pivot or like peak in between. So but for like the others, like you can find peak, like 5 is the peak, and then like let's say 4 is the peak, or 5 is the peak, something like that. So like here's like 1 to 4 is strictly increasing, and then start from 4, it doesn't increase anymore, it suddenly decrease. So you know like 4 is the peak. So it's something like that lah. So if you try to do 3, 2, 1, it doesn't work. So what we have to do is, like, if we wasn't able to find a black sheep, so let's say if FBS equals to -1, I would just reverse the whole array, num start kin to num start n, then I'll just return. Like what that does is that I already found like I cannot find the first black sheep. Then I know it's always like 3, 2, 1 because there's no black sheep. I can't find a black sheep. That's why I initialized it to -1 so I can check for this condition. So in this special case, I'll just have to reverse the whole array because like when it's largest, the next permutation is always like the first one. So that's how this algorithm works. If you think about this algorithm is very efficient where you don't have to do brute force. If you have to do brute force, like you have to do this much calculation. But if you're using this algorithm, what you have to do is just it's sort of like a 2-pointer thing, but it's not exactly a 2-pointer. Like you have to find the first pivot point, then you find the second pivot point, swap them and reverse. So this operation is much more efficient if we were to use it somehow. So let me just try to submit this. This should work, and it should just run fine with everything. Okay, so there's a wrong answer. Let's see. So input is 1, 2, 3, output 3, 2, 1. Probably we have some part. Oh, sorry. I'm using equal sign here. It's actually equality sign. So let's run it again. It should be equal to -1 instead of like equals -1. Yeah, so you can see like this is how we can do this next permutation. Actually, this question is not an easy question. Like even it's a medium question, right? And if you look at like the problems, that's why I'm finding it a bit hard to like explain the whole thing because you really have to understand the question really well. Say if I go medium difficult, it's not the highest passing rate. If I look at next permutation, there's only like 35% people can pass this medium question. So it's actually like the harder side of like the medium question. But it's not using a very bombastic data structure of like stuff. It's basically just array. You're still doing stuff with array. It's just that you have to really change your brain, like thinking, like finding the pattern. Because like the thing with like doing algorithm is where if you can find a pattern, you can devise like an algorithm, then you can solve things very efficiently. So yeah, so basically this is like the solution for next presentation. And let me see if there's any question. Is there any question? These two problems that I'm bringing out. Okay. So if there's not any question, then I think we done our session today, and I'll upload the solution to GitHub later. And yeah, thanks everyone for joining. Bye.